All right, folks, welcome to our super fun lecture. The captions on. So this is for geomorphology and hydrology. I'm going to talk about the river dynamics book, and we're going to start with chapter 5. Share my screen. All right, going. Okay, so this is all about sediment transport. So really, it's a fundamental process that, forms the channel and its behavior. Um, as we've talked about before, it moves rocks, minerals, and organic material like fish, critters, microbes, and whatnot just through the water. So there's a lot of material flux, and I'm sure you've seen this, in rivers, depending on the dissolved um, organic matter, we have suspended matter, and then we have what we call bed material. And so the material flux it depends on where it's coming from, what the mechanism is, and then how much energy is in the river. So a pretty big source of this, of sediment, is transferred rivers. And here we see this on the coast, right? We've also seen it when we went up to Owens Valley, and you see where those historic fluvial deposits have happened. And so it has a lot to do with, the hill slope, what the channel banks look like, if there's an overbank like what we saw, what kind of upstream inputs there are. All of these things, oh, excuse me, contribute to the different sediment load. So you can see by the chart here is the size of the sediment definitely has a difference, right? Clay and silt are going to move pretty quick, right? Through sheet wash, erosion, whatnot. It takes a little bit more mass movement for gravel and whatnot to happen. So you have to see erosion really happen to see those bigger chunks move along. When we talk about wash load, we're talking about the fine grained sediment. Usually it's not in the bed, it just is kind of carried through the river. So it's always kind of moving, rocking and rolling around in the water. Then we have something called a hyperconcentrated flow. And this is when a ton of sediment is in the water. So it's way higher than normal, but it's not like a full, just crazy debris flow. So it's when you have too much sediment moving. The bed material load is really the amount of transported particles that are picked up from the bed and moved down, like they're suspended during like a heavy storm or something and then moved down the river. And that suspension usually is that fine sediment, right? And so it really depends on how much turbulence there is and how big the particles are. If it's clay versus silt or sand, right? It's all going to make a difference. Bed load is just defined as that coarse material that rolls along the bottom of the river, okay? And it really only moves when the flow exceeds that entrainment threshold. So, what are the different factors that influence the transport? Okay, obviously it depends on turbulence, particle size, okay, water viscosity, and then the flow, velocity, right? So, how fast is the river moving? Are they fine sediments or heavier particle sizes? Obviously, the finer sediments are much, oh, excuse me, easier to move. It doesn't take as much energy, and then they remain suspended. So how does that work with discharge, right? So when you have this big discharge, it usually pushes a ton of suspended sediment through. And that's what they talked about a little bit up at the Owens River about the clean out, right? So you get that big rain, it pushes a whole bunch of sediment through. But the relationship to a big discharge is nonlinear, and it really depends on the sediment source, right? It depends on what kind of sediment it's going to be. Here's a chart showing the travel times of water versus sediment. And so you can see water obviously moves a lot faster, especially, oh, excuse me, than like the bed material. So suspended sediment moves right along with the water, but it kind of lags, right, when there's those ebbs and flows or little eddies and whatnot in the river. So we talk about the first flush phenomenon. Talked about this a little bit up at Owens River. When you have a big storm event early on, it basically gets all of that sediment and just plows it down through the channel. Okay. And then there's a lot of erosion and it just moves all kinds of stuff down the channel. So then we have what's called hysteresis, and that has to do when sediment concentrations differ basically on the hydrograph. So we've seen the hydrograph, okay? And so you see sediment concentrations high or low based on the different pieces of the hydrograph, all right? Then we have something called fingerprinting, and this really helps us trace where the sediment comes from, okay? So that would matter, say, if you were wondering where all this fine sediment or large rocks came from downriver. It really can show you the patterns of hysteresis during these big rain events, and this is how you can forecast what's going to happen. There are some factors, right, that we've talked about before. Vegetation, how intense is the storm? What is the soil like? What's the land use around it? And all these pre-existing conditions or antecedent conditions based on before we get that big rain, right? What does it look like? What does the landscape look like? All of these are different factors. And then, of course, seasonality, right? Like how often do we have storms? Is there a big snow melt like that they did up in Owens River? Does it really just happen seasonally? Depends on the vegetation, those kinds of things. And then really getting that bed material up and going is when the shear stress exceeds the critical threshold for the particle size. Basically, when there's enough force, right, it can push the particles down. And that's all influenced by the flow strength of the water and the turbulence. So you can see these forces acting on a riverbed, obviously are gravity, drag, a little bit of lift, and then friction. All of these things really work together to move the bedrock, right? The underneath, and because it's entrained in there and it's resisting being moved. So when it's small enough and you have enough push, that's off they go. So don't forget our bed shear stress, which is T, is calculated as T equals PGRS, where R is the hydraulic radius and S is the slope. So we have this critical shear stress. Basically, each grain size, you can think about all the different types of sand and rocks and whatnot in a river, each one has a different grain size, okay? So they each have a threshold of stress that they need to have before they can move. So it really depends on not just their size, but their density and their fluid properties to see, how much it's going to take to pick them up and take them down the river. And then you have boundary roughness, right? So rougher beds increase that turbulence. So you have the water dip and go up and it creates that backflow. And then it really produces more resistance and particle entrainment in that area, but then also increases the turbulence around it. So if you think about all the different pieces of that. So incipient motion is when the sediment hits that threshold and it starts to move, okay? And that's usually, they define it by about 50% mobility. So when that rock starts to wiggle, wiggle, wiggle and starts to move forward, that's that incipient motion threshold. Entrainment, when we're mixing all the different grain sizes and they're hiding and they kind of stick out, and then you wash all the fine sediment out, and now all the rocks are showing. Or there's one rock and the water's getting hit by it, but behind it a whole bunch of sand is sitting there. So that's what they're talking about here. The pivoting angle is really just the balance between what it takes to lift that grain or that rock and the resistance it has, okay? So obviously the higher angles, so the more upright it is, that's a more stable grain rather than, more of like a 30-degree angle or say 12-degree angle. You can think about the water can go around it and pick it up much easier than if it's, standing up straight. Smaller grains always have lower pivoting angles, and they're much easier to be picked up unless they're hidden behind the bigger grains or the bigger boulders. So we use this critical shear stress to normalize it across all the different systems. Okay, so we're looking at a lot of different rivers, different systems. We're using what we call critical shear stress without dimensions. Then we have something called entrainment, and that's really driven by bigger flows. Okay, so we remember what a step pool is, or those rifle pools where the river goes along and then it drops off, and then you have this pooling area. So that's where it entrains or entraps, right? The gravel and whatnot. And that usually happens when there's a high flow and it creates that crashing down. It creates kind of a dip in the bottom of the river. Then you have sand bed entrainment, and this is just has to do with the size, basically sand size, because they have lower thresholds and they tend to move no matter how slow or fast the river is moving. So it's a sand thing. And then we have these different kinds of metrics that we look at that are beyond what we're just looking at for shear stress. So it can be impulse and bed stability. You can't just use shear stress to predict like what's going to move and what's not going to move. It has to do with a lot of other things, right, going on in the river. It can't just be one thing of shear stress. So we have the impulse concept, and that's when we put together force and time. So it takes a sustained force over time. So say you're standing there and your friend starts to push you, you would probably hold up for a while, right? Until that person leans into you and pushes and pushes and pushes. Eventually you're going to get tired and go. Same kind of concept. And then we have turbulence. So those turbulent bursts and then the eddies that swirl the water around, it lifts particles even when it's not at shear stress, like critical shear stress, just based on that water movement and kind of like shifting and swipping around, and it picks things up and moves it out. And that's just all what this diagram is. Um, Here are a couple cool pictures of moving. It kind of talks about like the water surface and the flow, how the shear layer goes down. You can get this little separation zone and it pushes it back up, and how it pushes up and moves rocks around underneath in the river. It's also fun if you want to look up some videos on this, it can show rocks wiggling and whatnot. You can always look up mountain streams, right, which we have done in Owens Valley, and look at the gravel and how it moves in chunks. Basically, when all the snow melts and it has enough of that turbulence and force to move those big gravel chunks instead of just the sand and the clay. We've also talked about alluvial channels. So in the Mississippi River, right, we see a ton of suspended transport rather, and then a lot of bed form development when the flow slows down. So you get that deposit of sand and whatnot in the centers of the channel, on the sides of the channel. So you kind of see when it's a sandy river versus a gravel river, very different movement and very different changes along the bed. So don't forget, bed shear stress is central to seeing what the sediment movement is going to be. You need to know that. And then you can look at the shields diagram in your book and kind of, go over that if you want to see that. But I think we've explained it. Really, you need to know mostly about critical shear for this chapter, incipient motion, that pivoting angle, and then any of the hiding effects when like stuff hides behind the bigger rocks. And that all has all of those things and how they influence entrainment of like the deposit of those sediments. Okay. The Rouse number really is it's a profiling equation to see, basically what the sediment suspension is going to be. I'm not going to make you learn how to do this. If you go on to more hydrology, it'll be good for you to know. So we have a difference between competence and capacity. So competence is really the largest grain a stream can move, and capacity is the total suspended load that it can carry. Effective discharge is really the flow that pushes the most sediment over time. So, like a big snow melt, right? It's going to come down, it's probably going to last for a bit, it's going to push a ton of sediment, and really get that big discharge out of the river. So we can model these things. They have done empirical models for flow conditions, right? That's why we use all the fun stuff in here. And part of that is in your book if you wanted to look at it more. If you wanted to go into grad school, you would be doing flow models for rivers and streams and whatnot, especially along the coast. And then, we've talked about land use change, right? So deforestation, what's that going to do, right? More sediment is going to be pushed through urbanization, right? We start straightening channels and tons of runoff, as well as agriculture, changing all those sediment supplies. So I want you to think about that, right? We're not just thinking about just the river, you have to think about everything that's around it and all the pathways. When we make a sediment budget, we're tracking the input and the output as well as the storage. So you have to think about like the water that's coming in, how much sediment is there, what's happening within the channel. You're going to have to look at different times of the year, and then you make those predictions based on all of those budgets. It's quite a bit to check out and do. And then, just like on the coast, rivers can vary habitats, right? So if you get a big flooding event, you can just suffocate out tons and tons of vegetation, any kind of organismal habitat, And then the other thing is if a ton of water comes through and there's not enough sediment, you can really get these big incisions, right? You can see the river really change and cut through places. And so we've seen some of that. We're going to learn how to do field measurements with Dr. O'Hyrick in a couple weeks. So we'll go over more of that then. And we can look at making sediment rating curves. And this just is about long-term monitoring and looking at the different rivers. And we talked about extreme events. And so that's it for this chapter. Oh, I need to go over the last slide. So the key things that you need to know about is sediment transport, right? It's dynamic, up and down. The space and time is variable, and this is a central focus of fluvial geomorphology, all right? I put a couple questions in here that could be on the test, so it's something that you can kind of think about and practice. All right, so that was chapter 5. So now we'll do chapter 6. Just here, so you can see. Sorry, my screen is being a little tricky. All right, so chapter 6 in our book is all about channel forming events. So we have to really understand what the flow frequency is to be able to do that geomorphic analysis. All right, so which flows really do the most work? Is it the big flows, right? The big massive runoff flows, or is it the slow and steady flows? And so that's what we're going to talk about. Really thinking about the magnitude and the frequency of things has to do with being able to explain the variability, right? You have to inform whoever your management is. What if you are worried about flooding or restoration, okay, and how the channel is going to change? So you have to be able to pay attention to that. Not everything is like the LA River, right, and cemented all the way through. So we see a lot of water delivery from the different drainage basins. So you have to look at your drainage basin and see where precipitation is going to come through, where the groundwater stash is, right? Any overland flow that might happen. What does your land cover look like? And the topography, is it flat? What's the slope look like? What does the soil look like around it? And then you have to think about the seasonality changes, right? So obviously we have the wetter months and the drier months. And then how is climate changing and what does the land use look like? How much storage do we have? Are there any diversions? Things like that. So when we're measuring this discharge, you have to do it over time. So discharge equals area times velocity. We'll use a stream gauge. You can measure the different stage and then convert it. We'll use a rating curve. This will be something fun we get to do. You all have seen the hydrographs, okay? So we look at that rising limb and falling limb. We have the center section where the lag to peak is. When we have that rainfall intensity super high, right? It's going up, 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 up. And then you have the response of the river. It doesn't immediately go faster in discharge. It takes a minute, right? It takes a minute to respond. So then you have that falling recession limb of the hydrograph. You know, this is pretty basic, right? So how do you make a hydrograph? You're basing it on rainfall. You're looking at the basin size, what kind of land use is around there, and what does the soil look like? So these are all factors that would influence that shape. We can have a lot of different networks looking at different flows, right? So we can have peak flow that could be post-peak precipitation. So then the discharge would be, down the line. We can see the difference in the splitting off of rivers. We can use that width, and base it on the distance. And so there's a lot of ways to figure out how to figure out the peak flow timing and what's going to happen in all the different networks for flow. So if you want to figure out the flow frequency, you're going to look at historical discharge data, right? You're going to see how much water has come down. And then you're going to look at planning for that, right? And so that's in meters cubed. That's the annual peak discharge. I think we did this in one of the labs, and then you can see if that we're going to exceed the probability, right? So if we're going to have a flood or not. Um, Annual maximum series is 1 peak per year. Okay. And I think this happens a lot more. So these are log Pearson type distributions. I'm not going to make you do this. We have longer records for certain places. And remember, if any of you can remember anything about statistics or any kind of measurement in general, 5 years is not a long time, right? We need 20, 50, 100 years of data in order to really make those estimates and figure out what it is that we're trying to say. When you're doing those flood analysis, you have to look at all the peaks that were above the threshold that you saw. So it's not just capturing the big floods, right? Like a huge storm. It's capturing those shorter floods, right? Like, oh, we got 10 inches, in a month and we had a little bit of flooding. So those are those lower magnitude floods, and we need to check those, right? Because that's how you can see that exceedance probability and what's going to push up your peaks to see what the flood frequency will be. So AMS really focuses on the extremes, okay, and the PDS reflects on full variability. So when we have more frequent moderate flows, you can really see that that's what changes the sediment more than like the big huge floods. All right. So yes, when you have a ton of water coming down, you'll see like big cuts in the riverside and whatnot, but maybe some landslides or something. But when we have the more often rain, that's when you see the really big changes in that river. You see sediment deposition, right? You see the channel change. You see the flow change. You see a decrease in that bed slope. You'll see drop falls. You see all kinds of cool stuff with that constant moderate flow. So when we're looking at the flow frequency, we have to look at the flow records, right? And then how long did the flow happen? And then to really be able to do that, to make that discharge analysis, you have to have all the pieces. So when we make those flow duration curves, you're basically showing a percent of time where the discharge equaled or exceeded the amount that it can handle. Okay. And so this really shows that variability in stream behavior, right? The high flow area is when there's a lot of discharge, with the low flow, and you can see where it may or may not exceed. So, when you have steep FDCs, you have a lot of runoff, right? So this is just a diagram here showing a really steep slope sending all the water down into the channel. Whereas if you have flatter ones, it's mostly about infiltration. So like say Santa Monica really bases theirs on infiltration through the blacktop and whatnot, things of that nature. The slope and flood frequency go together. We have steeper slopes when we have a big storm, and then flat slopes when we have that more regulated flow. So then we have something called the dominant discharge concept. And so that's really what we're tracking when we're looking at sediments over long periods of time. It usually matches the discharge in stable systems, like as long as there's not some big crazy event, this is the kind of thing that you see, and this is what you can measure and give the probability for discharge. So when we have bank full discharge, that means that the discharge is all the way to the top of the bank. Okay, so you can see that you have the floodplain where the trees are, and that's the bank full width there. But then if it goes above the tree, right, that's where you have that flood. And so this usually happens within a 1 or 2 year interval. Okay, so where you get that water is all the way up to the banks, but it does not flood. Okay, that's called bank full discharge. So in order to determine whether or not a channel is full, okay, you're looking at slope breaks, vegetation, and sediment. All right, we're always looking at those factors because that's what matters where the water goes, right? So there can be complications. Humans get in there. Sometimes there's instability in the soil. You can see in this graph or in this photo rather, the black line is actually where the bank full is. But you can see there's a lot of chunks, benches, and whatnot that have been cut out of this particular channel. So a lot of times, whenever the bank full happens, that's also, the overlap for that discharge. The only time we see that not happen usually is in disturbed systems, and then, a disturbed system. So what would cause that, right? Agriculture, land changes, etc. So here you can see in A, you have a fairly natural channel. It's meandering. In B, that's definitely like on the side of ag or something. Then we have C with a super steep slope, so you can see the changes there. And then D, which is a really flat channel. Oh, excuse me. So, discharge is what moves our sediment, which we were talking about in the last chapter. And so we need to look at sediment rating curves and the flow records to figure out what is going to happen geomorphologically. So we have three different kinds of discharge. You have the dominant discharge, bank full, and then effective discharge. They're slightly related, but they're basically to inform how we understand rivers and how they function. Okay, so it all has to do with width and depth, and the bench index, working out the numbers. I'm not going to make you learn how to do this in this class. We also have what's called equilibrium adjustments. So gravel beds adjust a lot, right? So beds and slope, bed load and slope all evolve really slowly. It's things like this don't change super fast over time unless there's human interaction. So you always have fastest flow at the top when the channel is straight, and then at the corners, the fastest flow is always on that inside curve. So, what we call the geomorphic effectiveness concept is when something really causes a big channel change. It's not always like a huge event or really long. It's just about timing, right? Like when you see a huge, maybe a lot of water really fast, rain for days and days, and it makes a big geomorphic change. So you see the sand and the rocks move and the channel changes. Um, the hard part about saying that everything is in a steady state is that we're not paying attention to the thresholds and all the recovery processes that happen within the river channel. And so, channels evolve, okay, through feedbacks, thresholds, small little incisions can create a big response, it can create a whole new tributary. And as we know, we can see that happening in water. So we can't just assume that things are going to be the same all the time. Landscaping or the land use around the rivers and the channels really affect that, like sediment availability, how much vegetation is there, are they all connected, and the more sensitive your system, the more hardy your plants are, right? It's not going to react as much, but if you have plants like we learned with the willows, if they get flooded for too long, they die, okay? So you think about the different landscape around and how that really is going to affect the geomorphic movement, right? Or the rocks and the dirt and how that's going to move the channel around. So these are your factors. It looks at confinement, duration of the flood, how much sediment there is, and then how much moisture was there beforehand. So you have high potential versus low potential in looking at floods. So the higher flood power you have and the longer duration, the more movement happens. So flood power is stream power times duration. Okay, and this is just a power per unit area of showing of how much movement, right? How much of the bed load you can push. You can see these are different, just a couple different pictures of what rivers look like after floods. So sometimes it widens, sometimes you see a big incision happen. You can see a bar created in certain areas. So it really just depends on the geomorphic setting, right? Like what does the bed load look like? What does the underneath look like? How much sediment is there? What kind of sediment? What does the vegetation look like? These are all just different pictures for you to take a look at. We have what's called valley confinement. So, if there's a river within a valley, it doesn't have anywhere to go, right? It's stuck within that valley. So that's what we call valley confinement. And that means it reduces lateral mobility. Lateral just means out to the side. Okay, right? It can only spread so far. If you're not within a in a valley, that's unconfined, and then you can really push your sediment around. The river can migrate and kind of go off this way or go off that way. Flood power, remember, is important. It has to have sustained flows in order to really push that sand around. Um, Remember, sustained moderate flows make way bigger morphological changes than the short, intense ones. Any, antecedent conditions, meaning like before the flood, okay? Also, those conditions really have something to do with the changes. So think about landslides, all right? If it's been raining for months and then all of a sudden we get a big rain, it's really possible that the soil is super wet and so it's going to move, okay? Um, or if we've been in a drought and all of a sudden we get a huge rain that causes some kind of flooding event, it's going to change because the soil is so dry it might just suck all the water right up and you'd have very little morphological response, meaning like a very little movement in the sand and in the rocks. So also we have to look at different systems. So dry and humid systems. We're in a pretty dry system up north. As you get closer to the water here in the ocean, we are more humid. We have different kinds of vegetation. So we see different sediment loads and different kinds of infiltration of that water. That's something that we learned about in the beginning. So all of those effects, right? All of the differences really affect the magnitude of the flood response that the setting is going to have. Okay, so I want you to think about this. Magnitude versus frequency really explain channel dynamics, meaning the more frequent, longer term is really the ones that change things morphologically. Okay. Effective discharge, bankful, and dominant discharges. You need to know what those mean and how they inform channel behavior and changes. You need to know what flood power is and how the landscape around it can be sensitive based on the system and how that can change. All right. All right, that's it for chapter 5 and 6. Let's see. I'm going to stop this one.